Thanks everyone for joining for the New Eagle webinar for November. This is a kind of, hopefully we'll have an interactive discussion today on MotoHawk. We've got Joe and myself here to kind of share some things that we've learned, and then hopefully we'll have some good Q&A. So I want to point out on the on your GoToWebinar panel, there's a questions panel, so go ahead and add questions there. If you have some already, you can start entering them now. We've got some content that we want to share. So we'll go through some tips that we have and some libraries, and we'll get started here in just a few minutes. If you have questions, go ahead and type them in, and we'll get started here in just a couple minutes. Okay, we're ready to get started. As I said, we're hoping that we get a good amount of questions, that this can be an interactive discussion. So I wanted to just give a little background. My name's Ben Hoffman. I'm a senior software engineer here at New Eagle. I actually hired into Mototron in 2004, and so I've been working with the MotoHawk tools as an application developer and also as a tools engineer for about 10 years now. And Joe Morbitzer's with me today. He's a senior application engineer here at New Eagle. He hired into Mototron in 2005, and so he's coming up on 10 years working with MotoHawk also. So I'm hoping that if you do have questions, that we'll be able to answer them, and if not, then we'll be able to follow up and provide the answers. So with that, I'm going to turn the mic over to Joe, and he's got some good content to present, and we'll answer questions as they come up. Thank you.
Okay, can everyone hear me? Okay. Thank you, Ben. My name is Joe Morbitzer. Sorry about that delay. Having some technical difficulties with the webinar GoToMeeting, but I think we're online now. So the title of this is MotoHawk User Tips and Libraries, and I put together an agenda hopefully just to sort of brain dump on you guys a lot of sort of best practices that I follow in creating MotoHawk projects and just writing code in general. And so as Ben said, definitely ask as many questions as necessary during this if you want any more detail on anything I'm talking about. So first I want to, so I think everyone here is somewhat familiar with MotoHawk. Right? This is not MotoHawk training, but you've all been using it a little bit. Sort of, again, just want to go over the best practices, and the first thing that I always really emphasize with people is the importance of the MotoHawk project directory. Sometimes when people create projects, they start out with this Simulink model just from MATLAB and add MotoHawk blocks from that. And that sometimes works, but the best way to really start a MotoHawk project is through MotoHawk project command in the MATLAB command window. And you type the name of the folder and run it. And I already ran this previously, and once you run it, it creates these files that you see here in what we call the project directory. And so the project directory contains all files for a given piece of software. It makes it a very handy way to share software within people. You can simply zip up the project directory, send it to someone, and then they can unzip it on their computer and open it up. And if they use the same MATLAB MotoHawk version, should see everything exactly the same as you do. So a lot of times when we work with customers and they're having an issue, we'll say, send us your project directory. And by that we mean to zip up this entire folder and send it to us. And so the project directory should have all files associated with this project in the folder. And the only exception to that would be basically the MotoHawk libraries and the MATLAB libraries and everything like that. But everything else, particularly to your project, should be in the project directory. And it's also very convenient for revision control. So at New Eagle, we use Tortoise SVN as repository to maintain version control of all of our software. And it would be much more difficult to make changes if, for a given project, we had, different files scattered different places in our computer. So with the project directory, you keep that same folder structure on your computer as well as in SVN, and it works out pretty nice. One thing that also I always like to tell people is that when you create a project directory, you get these underscore close and underscore setup files, and we think it's pretty good practice to relabel those as model underscore close and model underscore setup. And the reason for that is, as you continue on with your project and perhaps have different model files in this project directory, you want each of those model files to reference these underscore close and underscore setup files. Now, if you left the name as is, then only the exact name of the model file that matches that would call those files. In this case, if if you have several different SLX files or model files, depending on which version of MATLAB you're on. For instance, maybe you have like a version 2 or a different software version. Each of these we'll call this model underscore set of models underscore close files. Now, as a review, what these files do, we can open up and take a look. Basically, when it runs, the main thing it does is it adds these subfolders to the MATLAB path. So just as a review, the MATLAB path is a list of all the folders on your computer that MATLAB will look in whenever your software calls a variable or a function or Simulink, the library block. So it'll all look for files in these folders that may contain those function files. And so we always emphasize the importance of keeping a clean path. If you have a lot of different project directories on here, et cetera, that's what we call a polluted path, and that's not a good practice, because if you have a file by the same name in 2 different places in MATLAB path, then there's a little uncertainty there as to which one of those is actually being used for your particular project. So the general rule, we really only like to see all the MATLAB installation, the MotoHawk installation, and then your current project directory in the MATLAB path. And so what the underscore setup file does is add your project directory, these files, to the MATLAB path when you open the file. And when you close the file, it removes those from the path automatically. And so because of that, another good practice on how to open a model file is to always open up MATLAB, point your current folder to the project directory like I did here, and then within MotoHawk, or within MATLAB itself, double-click your model file or SLX file and open it up. And this would be opposed to double-clicking this from like a Windows Explorer window, where if you do it that way, these files might not be called correctly. You might not get your project directory put on the path, and then you would have update errors and whatnot.
Hey Joe, before we move on to the next one, can you show where these the model setup script is executed from, or how does it get called?
Yeah, definitely. So actually, in every Simulink file that's created from the MotoHawk project command, if you right-click somewhere in the white space of your model and go to Model Properties, go to the Callbacks tab, you can see that there's some commands here to when the model is either loaded or initialized. It tries calling the underscore setup file. And again, this is why I recommended making the name of it model underscore setup, because it will look for the exact name of the file underscore setup. And then when you close the function, it calls the model underscore close file. So again, that's another reason to always start a project using the MotoHawk project command, so that automatically you get a model file that has these commands already in it.
Hey, before we move to the next topic, we do have a few questions. The first is, can we do real-time debugging using MotoHawk? So the answer to that is yes. There's a few different ways. There's a white paper on our wiki site that shows, it describes the MotoHawk application monitor. So Joe, can you pull up the wiki and go to the system debug blocks? or just type in system debug. I should point out the wiki has a wealth of information that's useful for learning about MotoHawk. But the first link there is a white paper, and that talks about debugging MotoHawk using the application monitor, and runs through the different knobs that are available for your debugging, and talks about the parameters that the application monitor exposes. And then as far as doing application-specific debugging, of course, there's probes, so you can use the MotoHawk probe and instrument your model, wherever there's some data in your model that you need to see. So that's two different ways to do some debugging. And of course, the application monitor is running. It does real-time checks on your the execution of your software, and then the probes are updated at your foreground rate or whatever rate the probe is residing within. We have a question about modified calibrations. So the question is, using MotoTune, can we flash into flash memory directly instead of RAM? So there's two different memory allocations for modules. There's a calibration version and a flash version. The calibratable modules have additional memory resources that can be changed by the calibration tool, and that can happen in real time, and you can kind of think of that as changing it in RAM, but it's persistent. So it's like a parallel EEPROM chip that's populated on those calibratable modules. The flash modules, those are what we call production modules. Those don't have that extra memory, and so in order to make changes to calibrations, we use a calibration management workflow called merge, and it takes the calibration settings and merges them into the flash that is part of the application executable that's downloaded during the programming. And so that's the way that you can modify calibrations for a production unit, and that is in fact adjusting the flash memory offline, and you come up with a new executable that can be programmed. So that's the questions that have come in so far. If you think of more, there's the question bar, so go ahead and we'll be happy to try and answer. Joe.
Okay. So moving on here, so talked about the project tree, MATLAB path. Just sort of emphasizing the fundamentals here, because we just want to try to set ourselves up for success as much as possible when doing a project. So these are things I'd definitely like to emphasize. Something else I always like to see, and I always have in my model, are these two blocks right here, the model version requirements block and the toolchain definition block. So these are obviously both in the MotoHawk library. Model version requirements is under extra development blocks, toolchain definitions under the build folder. Model version requirements allows you to either exactly match or newer, match or older, a specific MATLAB version and MotoHawk version. And so this is very important because especially if you're working with several, if you're working in a team, everyone wants to be on the same MATLAB MotoHawk version, and you would not want someone else on the team opening up your model in a different version, saving it, and then you taking their model and then opening up in yours, and then things may be different. So at a minimum, if that happens, you might see a lot of warnings on your MATLAB command window saying, either a mask parameter of a block is not found anymore because it was there and then was deleted. So that's somewhat harmless. At a worst case, some blocks may be totally changed. So there's some both MotoHawk and Simulink blocks that from different versions sort of get totally redesigned and do not open up even remotely close in different versions. So I think one instance of that is a Simulink selector block. The older version, the newer version are quite different, and if you configured it how you wanted in an older version and opened it up in a newer version, it sort of reverts to its defaults for the newer version, which is not going to function the same or function the way you want it. And so that can be, pretty dangerous. You might have a chunk of your software you think is validated and working, and simply by saving it a different MATLAB version, you could, get yourself in some trouble there. So, so we highly emphasize putting a model version requirements block in every both model file and library file that you're using in a project directory. And what this will do, if these requirements aren't met, you won't be able to save the file. So it'll prevent saving in different versions. And then additionally, the toolchain definition file specifies your compiler. And that's also something important when sharing files, or in the case of if you have a long-term customer that only visits their software every once in a while, and maybe there's some turnover in the company. So, person A opens the software a couple years ago, person B opens it up this year, they're going to want to know what compiler was used previously on this. By default, MotoHawk uses Green Hills if you have Green Hills installed on your computer. But if you're using GCC, you need to point to it directly through this toolchain definition block. Okay, next topic I want to talk about is model architecture. And so model architecture is definitely a debatable topic, but we found over the years that sort of a really nice way to, at a high level, organize your model is through sort of a sensors, control, actuators flow of the model. And so at the highest level, we typically organize our model sensors, which would have all sensor characterizations, so reading all your inputs, characterizing those into engineering values, and additionally reading CAN message inputs, putting all those values on a bus, and then those values move into your control block. So in the control subsystem, you may have what we call virtual sensors, which would be like processing of your raw input values. So just basically, secondary calculations to calculate variables that you don't directly measure, but that you want to use throughout the rest of your code. And then it would also include, your basic control logics. So whether that's, like if-then-else statements, a lot of logical operators, or PID controllers, whatever would be in your control for your given application, that would reside under here. Additionally, we put things like component characterization, so for different components, how to translate your control commands into like a duty cycle or Boolean, whatever would, however that actuator is going to be controlled. And then in the actuator subsystem, we have the actual, PWM block or discrete out block, as well as CAN message transmit blocks. So that's sort of at a high level, and then at a lower level, it's pretty application specific. But the one thing we always try to emphasize is that, it's important just to be really organized with your architecture. So everyone has sort of a different coding style, and that's pretty hard to make consistent across a company. And by the coding style, I mean, at the at the lowest level, how you would code particular logic. But what everyone can do is sort of just try to maintain an organized architecture. So have subsystems logically ordered and logically labeled throughout the model. One thing we always like to do is use bus creators and bus selectors sort of to their full potential. So So as an example here, and just as a summary, bus creator, bus selector are sort of different than the MUX blocks in Simulink, whereas the MUX blocks create actually a vector of inputs that all need to be the same data type. A bus creator just takes all your signals, which may be different data types and different sizes, and places them into this bus, which then can be, you can pick those signals off later using a bus selector. But we emphasize using the bus, bus creators a lot just to minimize the number of lines you have traveling throughout your model. So I always like to sort of put everything on the bus, and then sort of at the last point where I need to pick it off the bus, I will. So that will just minimize, many lines, and it'll sort of mitigate the chances that your model looks, like a bowl of spaghetti. One thing we always like to emphasize is you should label your lines with both a name and a units, just so it's very easy to see you downstream when you're picking these signals off the bus, what the units are. If not, you need to manually navigate back upstream and look at where the signal's created to figure that out, and that's just tedious and leads to errors. Another thing we like to recommend is always naming the signal line the same as a probe that may be on it. Again, this just makes it easier for people to, if you're in MotoTune looking at the name of a probe, you're trying to troubleshoot something in your model, it's easy to search for the same name and just creates less confusion. When using an override in a probe, we always recommend that the probe goes after the override, sort of the probe being the final, the actual value of the signal, and it's not changed anywhere else. So if you put the probe before, then you could change the value with the override, and it wouldn't be reflected in the probe. So we recommend the probe after. And additionally, again, the override name the same as the probe name. Overrides are something that we recommend placing in the model where strategically appropriate. So I think the practice we typically follow would be, at least every sensor input, every CAN input. So this would let you sort of test functionality without actually having to be actually receiving CAN inputs or physically connected to a sensor if you wanted to see how things react in your model based on different inputs. Definitely overrides on every output, so you can actuate outputs to test things. So like an override on a duty cycle or a PWM output, or an override on a discrete output. And then overrides sort of other, just strategically placing your model other places when appropriate. So we'd probably do it after, if you have logic determine sort of like a state of a system, we'd have an override there. We'd have overrides, well, I mean, it's sort of application specific, but the main thing to think about is if you're in MotoTune and you're on the field and you sort of want to test something, but it's not convenient to prompt something through a combination of inputs, where would it be convenient to have these overrides?
Joe, one comment there on the overrides. Strategically placed overrides can enhance the testability of your system. So if you're using the NewEagle automated testing tool, putting overrides in the right spots can allow you to test the tool in an automated, or test the software in an automated fashion, versus like a vehicle testing where you have to physically manipulate the vehicle. If overrides can be used to allow the logic to be exercised in an automated fashion. Before we move on to the next one, there's a few questions also. So we have a question that we'll touch on in a little bit when we talk about model documentation. The question is about the banner at the top of the model. So Joe, if you navigate up one level or so, there's a banner that comes from something called Autodoc, and we'll touch on that in a little bit about how to change that. Another question is related to the output files. It seems that MotoTune likes to have the DLL and SRZ file in programs in TDB DLL. Like to put them in a different directory. Yes, you can if you right-click on the Moto server icon in the task tray, you can change where MotoTune looks for those. But I don't know of a way to change where MotoHawk puts those. MotoHawk always puts them in the C ECU files. So if you go to locations right there, yep. So you can adjust where things are where things are being looked for right there. The next question, can the model be multitasking? Joe, I don't know if you're planning to touch on that, but you can certainly have multiple triggers in your model that can allow different code to execute at different rates. If we look here at the top of the model, there's a trigger block. The template model only has one trigger block, but you can copy multiple trigger blocks in and specify those to run at different rates. So we kind of touched on buses. The question was related to any comments on passing data using buses or data stores. We found that buses allow you to organize the data that's flowing through your model. The data store, a MotoHawk data store, in reality is a global, and so you can read in the literature about people's comments on using globals. My view is that the MotoHawk data store provides, well, it does provide a global. There's a lot more checking that's done on it with data types and naming. So it's not as frowned upon as like a C global would be. Can a MotoHawk ECU drive any relays if we enable digital output? Certainly, digital outputs can be used to drive relays. You want to make sure the current capacity matches up with the device that you're driving. For instance, a TTL level output won't be able to handle a big relay. Okay, we'll touch on the remaining questions in a little bit, but definitely keep asking.
Thanks, Ben. And something else I just wanted to mention, there's a question on the buses versus data stores. And so in our models, we definitely use both. Both have their place and both are appropriate for different things. One thing to remember with having logic that, you know, is all sort of on these lines is that it's very easy to dictate order. So something that the order is that whatever happens upstream happens first relative to something downstream on the same line. And when you use data stores, or it says the MotoHawk, you know, data def, data read, data write, you have other little chunks of code that you might not necessarily know when it happens relative to other things. And so it's just important to be aware of that. Now you can, I mean, there's a couple of considerations there. One is, if it doesn't matter, then it doesn't really matter. You know, a lot of our models run at 5 milliseconds, so sometimes it's not even worth worrying about if it happens before or after something else in the 5 millisecond loop, because if it happens, you know, it's going to happen within 5 milliseconds. So it only matters if it really matters relative to like the math and logic that's going on in the model, if that makes sense. Now there's one way, let me bring in a couple blocks here. So for instance, if you're using a data read, and a data write, both for the same piece of data, this would be in an instance where you're sort of confused, like what would happen first, what would happen second. And there is one way you can dictate what would happen first and second. If you right-click the block and go to Properties, you can specify a priority. And so this is sort of like a not too commonly used thing. It's sort of a trick that's sort of underneath the hood. Like you put a priority here and then you press OK, and it's not relevant just looking at the block. You'd have to right-click and go back here to see if there's a priority or not. So be careful using it. You don't want to accidentally have a bunch of things with different priorities on your model without knowing it. But if I wanted to, say, write this piece of data first, then read it, or read, then write. So if I wanted to read, then write, I could specify this with priority of 0, which is a higher priority, and then give this one a priority of 1. And then I can use let's see, I forget where this is in this version. Here it is. Sorted execution order. This is something you enable in your model, and I do frequently. You can see, oops, well, I got an update error because I don't have the data depth in here. Let me bring that in here. Okay, so you can see through these little labels, execution order. So 5:32, 21. So 5 would be so different subsystems and functions are given different sort of like first numbers, and then the second number is sort of within this function what happens first and second. So we can see here that the 21 happens first, then the 22nd happens. And so if we wanted to reverse those, do an update, we can see that the order then is reversed. So that's one way to dictate execution order of data reads and writes if you need to. Okay, I wanted to talk about stateflow a little bit. Stateflow is a great tool that's built into Simulink. So it's not a MotoHawk thing, but there's a Simulink thing. It can be used, well, sometimes it's used in the wrong fashion. So I sort of want to talk about like when it's appropriate to use stateflow. And so I made a sort of an example function here of just sample logic where there's a couple systems and subsystems and super systems, and maybe in one of the systems there's this timer that's going, and when you reach the threshold you move into this system, and then you look for another input to go in a different subsystem, and from within this system if the input changes to 1, so that's like sort of like a rising edge trigger, you go to this super system, and then you only move out on this criteria. So it's sort of logic like this where stateflow is very appropriate because you have a bunch of systems and subsystems and then maybe complicated criteria to move from one to another. That if I try to place logic like this in a Simulink itself using if-thens, ors, and everything, it could get pretty messy looking and very difficult to read. So stateflow is appropriate for when you have these different, very defined states. Some people use stateflow to just do like basic math and stuff, and although it works, it's not really what we'd recommend doing. So if you're just using stateflow to do sort of some like basic math or very simple logic that can be used, that can be done pretty clearly just using logical operator blocks, then I would do that in Simulink itself. but stateflow is appropriate when you sort of reach some certain level of complexity, and that complexity to make it too hard to read your logic in Simulink itself. And so that line is sort of, variable. I guess it depends, totally depends on the user when they want to use stateflow or not. But so I just want to give an example here where I definitely think it would be appropriate to use stateflow. Couple good practices with stateflow is, use the model browser to sort of define your inputs and outputs here. I always like to define inputs as sort of inheriting the same data type as Simulink. Although you can explicitly give it a data type, that doesn't totally make sense to me because it should have already been created in Simulink as what you want it to be. So all my inputs, I always I always input, inherit the size, inherit the data type. On the other hand, all outputs should be explicitly specified in terms of size and data type. Same with all local variables. And of course, just like in the model, you should do math on like variable types, and you should pay attention to your data types within Simulink. One thing I always like to do with timers within data type is sort of keep it as sort of a count. So in this case, where I have a timer, I'm really just adding 1 to my timer, compared against this threshold. But then that threshold, I give a MotoTune gain as my sample time of the model, or how how often the foreground rate's running. And so one reason I like doing this is that I might, instead of putting 005, I might make this a variable such as sample time. And then I might specify this sample time variable in the highest level mask of the foreground rate. And by doing that, if I need to change the data type of my model, I just change it right at that high subsystem, and then it's propagated down everywhere it's needed. So that's one reason why, even though for this example I put 005 here, typically I wouldn't always recommend doing that, because if you had to change the data type, sampling rate, you'd have to search throughout the whole model, make sure you find all those instances and change them. And so that can lead to mistakes. Okay, so definitely if there's any stateflow questions, make sure to send us those.
Joe, a couple questions. So I know you're going to talk a little bit about CAN in a bit, so we'll hold off on that one. Can you open a probe, kind of show how the data type or the signal's defined? So you can see here you put the name. That's the minimum that you need to specify this. There are other things you can do. For instance, if this was a Boolean condition and you wanted to have it say true or false in MotoTune, you could see their view value as, and if you go where it says view value as, you go to instead of number, you show enumeration. That makes the next field highlighted, and you can see for a value of 0, you'd see disabled in MotoTune, and you'd see enabled if the value was 1. There's a number of other things that you can specify related to how this is exposed in the calibration tool, such as the MotoTune precision and the group, which is where it's going to show up in MotoTune. I think Joe's going to talk a little bit about structuring data for MotoTune in a bit. The question about enumeration. So can you use enumerations for Boolean overrides, data stores, and calibration blocks? So we just touched on how you specify enumerations. If you click the help for this block, it shows you more about how to specify enumerations and more complex enumerations, and specifically for if you have a table type or something. So that's kind of a quick. You can see that there's quite a. If you go to the enumeration area there, Joe, there's a lengthy description of how to set that up. So I'd refer you to that. Regarding the simulation behavior of data stores. So when using MotoHawk data stores, does it behave as a normal Simulink data store during simulation? MotoHawk data stores should simulate. And so if you write into the simulation, if you write into a data write block, the value should show up on your data read blocks elsewhere in the model, just like you would expect. Question, is there any method to detect the time taken for execution of any subsystem? There's a method built into the application monitor which allows for you to know what percentage of time is being used by a particular task. But as regards an individual subsystem, what I've done in the past is use the MotoHawk time blocks, and I will use a function call generator and pass that into a demux, and that the demux of a function call allows you to configure what is going to execute next, so the order of execution. So I will calculate the start time in the first one, execute the subsystem, and then in the third one I'll make a calculation of the delta between those. So that's one way that you can, in your application, generally you'd only do that for debugging purposes, but so you wouldn't probably have that in a production app, but it can be useful to use those blocks to calculate how long a particular subsystem is taking. We kind of talked about the priority blocks, and Joe showed you in the mask of the data def blocks, the data read, data write, how to specify a priority so that the execution order is affected. The Simulink or the MotoHawk trigger blocks actually have on the front of the mask, so it's not hidden at all. They have a priority. Joe, can you bring up the MotoHawk trigger? So if you have multiple triggers at the top level of your model, you can specify using the priority there which one is going to execute first. So a 0 priority will execute before priority 1, for instance. Okay, so a question, on the highest level of the Simulink model, I could see the RAM, EEPROM, etc. parameters. How do you set the starting address and size of each memory? So you don't. MotoHawk handles that for you. For instance, if you specify an EEPROM, like a non-volatile data store, MotoHawk needs to specify a couple of different memory locations for that. It needs to specify one location in Flash, which contains the default value for that non-volatile storage. It needs to set aside some RAM memory so that you can work with it in real time, and it also needs to then store that at some point to EEPROM. And so it would be quite complex to allow the application developer to specify that, and then to have them consider managing the data memory locations across the whole model. So that's all managed automatically. Does MotoHawk provide toolboxes for fixed point design? You know, we do have a block set called that we call the B numbers, and it allows you to do fixed point. Joe probably can dive more into that. I think that's a topic that we could spend a whole webinar on by itself. I suspect that you might be able to find some more information on the wiki about the B blocks. If not, I'll take a note of that one. That's a potential candidate for another webinar. Can you show how to configure the EEPROM and Flash? So, Joe, if you want to pull up the maybe in the target definition block. So you can specify the memory layout of your ECU there with the memory layout. As I kind of touched on this before, you've got a dev or a calibratable module or a production module. So the calibratable module has that additional memory that allows you to calibrate online. So that's one way to select. Now, as regarding a particular data store, Joe, if you want to go to the data def that you have there, double click on the. So if you want to specify that a value is a calibratable constant, you can select constant there. This is a little different than the Simulink constant because the value here is able to be modified after the build in an offline manner with the calibration tool. So you can merge in a different value. So that's slightly different than a Simulink constant, which is fixed at build time. Volatile just means that it's a RAM variable, so it reverts to its default value during a power cycle. Non-volatile, it's got a default value on startup, and when you have a controlled shutdown, it'll store the value away and return that value when the ECU wakes up the next time. Fixed non-volatile is a specialized category of that same non-volatile, and that allows you to retain memory across the programming cycle. So the non-volatile allows you to retain memory values across the power cycle. Fixed non-volatile allows you to retain things across the programming cycle. And that's a specialized category of memory that is you need to be very careful in configuring it and designing the structure for that, because for backwards compatibility reasons, it's a specified area of features, and you need to do research on how to use it before going to production, I'd say. Okay, so that's the questions for now.
All right. Moving on, I wanted to talk about libraries a little bit. So I put together a little sample library here. Now, I'm sure you guys have used, hopefully have used libraries within your project. We use them very frequently, and the purpose of them is basically any block in your model that you use maybe even more than once should be in the library. So anytime you have code that you want to duplicate, or you have a block you use frequently from project to project, you might want to make that a library block. And what the libraries do is it basically creates sort of this reference block for all instances of that block in the model, so that when the instances are linked to the library block, you make a change in the library and they're propagated to every instance in the model. And further, as I'm sure you know, you can disable that link in the model itself, make a change, and then push those changes back into the library block. And then on the next update, all versions of that block will get those changes. One great thing about using library blocks is that sort of just over time, you sort of start building up this library that you just have your commonly used blocks in. Project to project, you might add more and more, just as the projects go on, as the years go on. And what you have at the end is sort of this, this set of blocks that you've used over and over and have validated through just use. And so you have a lot of confidence in these blocks. And when you start doing projects in the future, it's more of sort of like putting blocks together as opposed to starting from ground up programming. So it's more of like putting a puzzle together instead of thinking of all the low-level details. You already have these blocks that do a lot of these functions. You just are piecing these blocks together now instead of starting from the ground up. So it allows you to be much more efficient and confident in your code. And so a couple examples here. this counter block is one that I use quite often.
Hey Joe, as you're on the topic of libraries, I should mention that you talked about building up libraries that you use from project to project. We offer some that we have built over the years on our website, and those are available for application development. And it's a great way to get a jump start if you're new to using MotoHawk. I think it's called the Foundation library, and it's kind of the foundation that we use to start when we do a new project.
Yeah, and I think actually several of these blocks are from the Foundation library blocks itself. So this counter is an example one. So what it does underneath is, it's pretty simple. It's simply sort of a counter or a timer that's compared to a threshold, and then the output is the relational operator there. And so it's simple, but this is, if you didn't have a library block for this and you had to code this up each time, at some point you'll make a mistake. So it's just nice to have this block that when it's enabled, you take the previous value and you add your increment to it. When the reset port is true, you reset back to an initial value. When you hit the threshold, it disables the counters to prevent overflow on this. And so, it's nice to have this block that, I know works, I know it's not going to overflow, it works as I need it to work. It's a block I made this mask for, so you guys probably remember from MotoHawk training, or you've probably used masks before. You can create a mask on a block where you input things like the initial value after reset, the increment value, and then the threshold information like the data type, the relational operator itself, help text and units for the threshold, a gain, a mode to group. That's all done by creating a mask and then adding the parameters here with a couple initialization tasks, such as setting the data type of the calibration and those couple constant blocks. So another example of a block I'd expect to come from a library to be like a PID block. So again, everyone knows how the PID block works. Look at the difference between a set point and actual value, and then you have, you multiply that by proportional gain to get a P term. You integrate that error term over time. You take the derivative of it, multiply it by its gain, you add them all up. So, it wouldn't be too hard to create this each time, but that's just time consuming and can lead to mistakes. So it's nice to have this one block, drop it in, and then interface is very well defined. So definitely send any follow-up questions on libraries to Ben, and we'll answer those. One other thing to note, I mentioned libraries are simply, what they do is just, if you look in the code gen, it's just repeating code. So it's typically not like a function. So some people think it's a lot more efficient in code gen. It's not really necessarily the case. It's really just more so this is going to work and you have confidence in it, and you're using validated blocks over and over. It really does not really make code gen anymore. Doesn't make your coding more efficient with respect to like using functions or something like that. Okay, next I wanted to talk about, okay, we're going to go to Ben.
So before we go to the next topic, a couple of questions came in regarding one was on the Foundation library, and is that something that we charge for? Definitely it represents a lot of reusable content that we've developed over the years, and so we do charge for it, but we think it provides an excellent jumpstart for anyone that's using MotoHawk. As in addition to the actual blocks that are in there, it shows you how to structure libraries, how to make calibratable, parameterizable library blocks. So it's a great, I think it's a great value. There's a question about MotoHawk. Does MotoHawk include all the libraries to access I/O on the control units? Certainly, MotoHawk provides the kind of the basic functional blocks that allow you to work with the I/O and the tasking inside your ECU. Joe, if you want to pull up the MotoHawk Simulink library interface, you can see it's quite extensive, the libraries that are provided by MotoHawk. So those are the, that's the full, and if you just go to like one of the I/O areas, you can see that, you know, there's lots of blocks. It's quite extensive. Definitely provides all the Legos that you need to build up the capability for a complex control algorithm. How can we read XDRP voltage being supplied by the controller to the sensors? Joe, I think that's probably like an analog input. Yeah. So just dragging an analog input block and then select that resource if you want to show how that's done. You're in a library. So you can kind of see here, if you're going to be working with the pins on the outside of the ECU, you use these blocks here, and this provides you the analog to digital counts for the XDRP resource there with the 5-volt reference. Great.
Ben mentioned the foundation block set, so actually this is it right here. So this is an example of like some of the libraries that we maintain. It has a lot of just, well, first of all, it has a lot of sensor characterization blocks, you know, for linear sensors or potentiometers or nonlinear sensors, discretes, and all those have diagnostics underneath them. Has output blocks for like PWM signals, some blocks to help with CAN, receiving the CAN messages. Then it has things like PID loops, a bunch of fault blocks, these counters, and just a bunch of other basic blocks that, you know, we typically use, you know, some more frequently than others, but typically use this foundation block set a lot when creating a model. Okay, I wanted to talk a little bit about a couple fault managers that are in MotoHawk. So there's two of them. There's the classic and the OBD fault manager. And so I just sort of wanted to quickly highlight some of the differences between them. So, you know, one goal of diagnostics is to, you know, quickly and reliably identify malfunctions that are in your system. And so these might be related to sensors or actuators, such as like inputs and outputs being open or shorted. These might be malfunctions on an actual component, such as, you know, in OBD land, we have all these major monitors that try to identify malfunctions within a component itself, such as like a catalyst. Or these may be malfunctions on our hardware. Maybe we're trying to detect if the processor or RAM or something like that is degraded in any respect. And so, you know, you'd have your fault logic, and then that logic would go into the fault def. And so both the classic and the OBD fault manager have this fault definition here. Both are very similar. They both have this X out of Y filter to say, you know, if I suspect the input 25 out of 50 times, then that's when I consider the malfunction to be actually present. So sort of like a confidence filter there. So the OBD block has the same, and it also has its drive cycle. So in OBD land, there's always talk about drive cycles and different statuses. So OBD has things like pending, confirmed, mill on, all these different statuses, and so the drive cycle is related to that. And so this, in conjunction with the drive cycle complete block, which you can trigger throughout your application, lets you sort of put in blocks that reflect these OBD statuses. Both have the typical fault action block, where another goal of diagnostics is to, once a malfunction has occurred, sort of maintain an acceptable level of system functionality and predictability. And so you'd use fault action blocks to, when a malfunction is detected, take some sort of action in your model. Or you'd use these fault action statuses blocks to sort of hard code a fault action and say, oh, if something's active, then, for instance, if a sensor input is open or shorted, send a default value throughout the model instead of sending your characterized value, because at that point that's sort of an invalid signal. So that'd be an example of a hard-coded fault action, whereas using the fault action blocks here, you create a calibratable fault action. Then in calibration, it can be tied to any fault definition under different conditions. Another goal of diagnostics would be to provide, both let the driver know or let the operator know that a fault has occurred. So you can use, fault action block to light a lamp or something like that. And then one of the most important functions of diagnostics is to provide information to the repair, the repair technician or the service community as to what went wrong and how to fix it. And so to do that, you would use, for instance, in J1939, you use these DM services, these diagnostic message services, such as DM1 to say what faults are currently confirmed on the vehicle. DM2 is previously active faults, and so there's a variety of those to communicate fault statuses through a scan tool to a service tech. A freeze frame would be another one of those. And so along those lines, that's another block set that New Eagle provides, is our J1939 block set. And that contains a number of J1939 functions, some of them being these DM services. And, using the blocks, it's very easy to implement, to integrate with OBD block set.
So I should mention here, when you implement a diagnostic strategy, the fault manager holds a lot of the information about the diagnostic status of your system, and oftentimes you need to communicate that per the regulations in your industry to a scan tool or for certifying bodies like EPA or CARB. And so if you're operating in light duty, the protocol that's used for that is the UDS light duty diagnostic protocol. And so since the fault manager has all that information, we the blocks, the UDS blocks, reach into the fault manager kind of under the covers and then generate the protocol messaging. And in the heavy duty space, you're going to be using J1939, and in the same way, since the fault manager already has all that information, the protocol blocks will reach in and kind of under the covers for you, create the protocol messaging according to the regulations. And so that if you're in that kind of market, definitely those blocks are the way to make the diagnostic information from within your controls available to a scan tool or a certifying certifying body. So those are also both well described on our wiki site, both the UDS block set and the J1939 block set. Definitely, if you're facing implementing those protocols, it really makes a good deal of sense to take a look at those first.
And one other thing I want to mention with the OBD block set is these custom fields. So this is a great feature of the OBD block set that allows you to append data to your fault manager. So if you remember with the classic fault manager, if you've ever seen it in MotoTune, it looks like it's a big structure. And there's no way to like add another field. If you wanted to, for whatever reason, if you're keeping track of like fault counts maybe or something, you'd like to add a field to that fault manager. There was no way to do that with the classic fault manager. But these custom field blocks with the OBD fault manager gives you that capability. And so you can add a custom field that would either be a calibration or volatile or non-volatile variable. An example of these used in conjunction with our J1939 block set would be we'd create a custom field calibration for SVN and FMI of each fault, because that information is what is communicated over DM1 and DM2 and all those services. And so somehow in your application you need a way to calibrate these SPN and FMI for each fault, and you do it through the custom field. Another way it's used, again, with J1939 is keeping track of occurrence counts, so how many times a fault has turned confirmed. That is also information that's communicated over J1939. And so we do that, again, using custom field, a volatile variable, and whenever the fault becomes confirmed in the application, we use the data read and write to simply increment that by 1. Yeah, so it would be non-volatile. And then the custom field, those 3 custom fields I described, the SPN, FMI, and occurrence counts, those really sort of work seamlessly with our J1939 block set. And so once the fields are defined in the application, and once you need to put a little code in to increment the occurrence counts, for instance, when necessary, but everything else is done underneath the hood.
Joe kind of dove into a little bit of some protocol-specific details there. I would mention that a couple months ago we did a webinar on the J1939, and so you can find the information about that and the presentation for that topic in detail there on our website.
Okay, moving on here. Definitely want to mention CAN communications a little bit, and wanted to show two ways of sending out a CAN message. So if you guys have used the CAN box in MotoHawk, you're probably familiar with the MotoHawk read CAN message, send CAN message, where you define your message to an M file, which is not too difficult to use and has its place for sure, but the industry standard is sort of moving towards these DVC files, which is a vector developed format for specifying a CAN message, both in terms of the CAN message ID and then also its content and all the fields and everything. And so New Eagle has developed this network toolbox where the interface, or from the model itself, it looks like the MotoHawk block and it functions the same, but the interface is different. You can point to an actual DVC file. In this case, we have a J1939 DVC file with all these messages, and you can pick whichever ones you want very conveniently, and the same options that you see in the MotoHawk block are on the New Eagle block, such as showing age count, data variable, etc.
Yeah, I should mention, kind of backing up a little bit, when you're doing CAN, you know, there's a lot of details with the way that the data is packed, and you know, things like endianness and offsetting and scaling of data as it is packed into the message that goes onto the CAN bus. You know, the interface that's provided in the model-based world using MotoHawk provides a nice abstraction for that, so that you don't have to actually deal with code for packing and unpacking. You can see here in these blocks that, you know, based on the DBC specification of the message, the block face indicates the bit packing that will be generated for you. A lot of times if you're implementing CAN messaging by hand, you spend a lot of time making sure that the output on the bus is correct according to the specification. You know, have you coded it correctly? By using these blocks, the MotoHawk blocks, yeah, you're taking advantage of the code generator to do that hard work. And we put an interface on the CAN blocks to read and the send and receive CAN messages that allow a DBC file, which is pretty much the standard now, to be used right in the model. Avoid a lot of issues with you know, accuracy in the incoming and outgoing messages.
Okay, so moving on to the next topic, I wanted to...
Before we move on to that, there was a question about how to schedule a CAN message. Say you got a couple different CAN messages and you want them to go out at different rates.
So you have several CAN messages, and the question is, you want to transmit them at different rates. So there's an option, and this option is both in the New Eagle block and the MotoHawk block. Yeah. Obviously it's in the SEM block. You can, for transmit, you can either use this -1, which indicates asynchronous, which would mean transmit whenever this block executes in code, which would basically mean transmit at whatever rate the foreground or the subsystem is being executed at. So whether it's foreground rate or maybe it's slowed down within that patient, but whenever this subsystem executes, transmit. Or you can put in milliseconds whatever transmit rate you may want. And so it's as simple as that. So one other thing I want to talk about was really quickly MotoTune and the importance of good MotoTune organization in the folder structure. So this is something that's sometimes people don't pay much attention to, because it's not something you really need to pay attention to when you're creating your model for functionality. But then when you actually build it and you get on the hardware and you open up MotoTune, it becomes important at that point. And if you don't try to at least, you know, be consistent in your folder structure, then it's really difficult to find your variables, both in a display and calibration. So something we typically do is definitely sensors, control actuators, you know, just like the model structure. Doesn't have to follow exactly, but so at the high level we have those categories. We also have like a diagnostics folder. The system folder is created automatically on a build. That creates a lot of variables that I just wanted to mention real quickly that are helpful in troubleshooting code. So if the application stopped for some reason, it will tell you. It will tell you here. There's also variables for where's that? For CPU idle time. So that's something during development that's nice to keep an eye on. So what percentage of the time is your CPU either idle or active? So a high idle time percentage is good. Well, I mean, it just means that, I don't know if it's good or bad. I'd say it's bad when it's getting very low. Then you might want to think about taking steps to either improve the efficiency of your code or slow down some tasks within your code. There's variables that show you stack usage, so you can, during development, if you get close to those, you can go back to your model and in the target depth block allocate more memory to those. And well, the application monitor that Ben mentioned earlier will trip if any of these are exceeded, plus or minus a little margin.
Yeah, so the variables that Joe's just pointing out there, at the beginning of the webinar we mentioned that white paper on the application monitor and debugging your application. These variables are described in more detail in that, and so if you're looking at using these, definitely get that white paper and read more about them.
Okay, so we have a couple more minutes here, and definitely send any more questions as they may come up. But I just wanted to talk about a couple properties, and I mean this is a couple like common things that people think about when they think about good code. So, you know, as a code, sort of a code design review, these are some things you just want to think about when you're making code. I always like to say code should be really robust, and you know, you hear that word a lot. But to me, that means a chunk of code should be able to handle any combination of inputs gracefully, and you shouldn't make any assumptions about what those inputs should be. You know, so for instance, you shouldn't assume the ranges. You know, a certain chunk of code should be able to handle inputs within the full range of whatever the data type those inputs are. You know, in a graceful manner. You should try to focus on modularity and portability of your code. So this relates to, you know, how easy is it to take a chunk of code from one model and transport it to another model. And the easier that is, the easier, you know, it is just in the future to create models. You can take code from other models, and that's really defined on how well you make your interfaces. So if for a given chunk of code you have a block that has, you know, it's all in a subsystem and the interface is really well defined, then it's pretty easy to move that code around. If it's very convoluted and sort of, you know, if the pieces are all over the place, then it's hard to do that. So always think about that. Think about what mask parameters you can add to a given chunk of code to sort of bring things that may change up to that mask, such as like sample time or MotoTune group, you know, anything that someone or an application might want to change for a given piece of code, try to bring that up to the mask. So next time you use it, you can just change it in the mask instead of having to dive deep and make the changes in every place within that chunk of code that needs to be changed. Good code is, you know, you can read it, so readability is something to always think about. Think about the next engineer that needs to read your code. So again, sort of everyone has a different style, but at a minimum what you can do is organize your code well, so at least they know what subsystem to look at for a given function. Good code is efficient, so it doesn't hog resources. You know, it's running when it needs to, and it's disabled when it doesn't need to run. So think about using enabled subsystems, stuff like that. And good code is, although this one is pretty subjective, you know, good code is elegant. So elegance is sort of a combination of simplicity and efficiency. You know, it shouldn't really be any more complicated than it needs to be, and it should be as efficient as possible.
Thanks, Joe. We have a few questions on the line, and we're getting to the end of the time we had scheduled for this, but we'll hang out for some questions. So take a few minutes if you have some. Joe, it'd be good to show the main power relay block. If you want to just open that up.
Yeah, so main power relay block, typically resides on the top level of your model. At least it does when you use MotoHawk Project to create a new model. And it's a MotoHawk block, as you can see with the gray background with red and black stripes. Now it's a little different than most MotoHawk blocks because it's simply a compilation of other blocks. So a lot of the MotoHawk blocks, as you will see, are really low-level blocks. They don't assume much about your application. They give you the tools to do what you need to do in the application. They give you the tools to interface with a piece of hardware. We always call MotoHawks sort of like the hooks into the operating system for a given piece of hardware. So it gives you the ability to work with hardware. Most other code in your model uses Simulink. But MotoHawk is more for like operating system type stuff. But anyway, so this block, again, is a little different because it is simply a compilation of other blocks. And it was created simply because it's a very commonly used block, and there would be a lot of support if the toolchain relied on people to make this block every time that they had a new application. But the main power relay block does a couple of things. On a power switch on, it will turn on the main power relay with a delay. So if you already have a MotoHawk application, you may recall that when you go key on, there's a little delay, and then the main power relay turns on. And then when you key off, there's also a little delay, and it turns off. That delay is done in the application here because, in fact, the main power relay itself, the discrete output, is in the application. It also, on a key off, runs a couple tasks here, the main ones being saving non-volatile. So this is where you save all your non-volatile variables to EEPROM, to the calling of this block. And then after that's done, it shuts down power, which basically turns off the module.
So I think that's enough of an overview for the main power relay. People that have a custom shutdown scheme oftentimes will break the library link and go under here and modify it. That's part of the reason why it's provided as it is here, as a part of a construction within Simulink, so that you can modify it if you need to. There's a question, how long does it normally take to store non-volatiles? That's going to vary based on a few things. One is how many non-volatiles do you have in your application, and the other is that the time to write non-volatiles is not deterministic. So what we typically do is give it a reasonable amount of time, enough that you're pretty sure, that it's going to be saved. So that is kind of an exercise in tuning the shutdown of your specific application. The other thing that you want to be careful about with non-volatiles is they have a limited lifetime. So we usually use like 100,000 writes as a if you've got a timer that, like an engine hours counter that you want to store, we generally do a calculation based on 100,000 write cycles, and make sure that the life of the module is going to be acceptable in some number of years or whatever is right for your application. Joe, can you touch on the AutoDoc blocks? The AutoDoc blocks are a way to provide documentation from your model. It's another thing that you can find on our web store under the MotoHawk libraries. But there was a question about the title banner there, and that it default says Woodward, and a lot of people may want to change that to their specific company logo and name.
Yeah, so AutoDoc is something I skipped over, but AutoDoc is it's a tool to provide both sort of in-model and out-of-model documentation. So you grab this AutoDoc block, and it sort of creates this border. Now, in recent versions of MATLAB, you can't see the side borders, unfortunately. But what it does is it attempts to sort of confine your code to this 8.5 by 11-ish size, such that when you can also run AutoDoc as a function in the command window to create a PDF of your model. So you just place these blocks out your model, you try to organize your code within the boundaries, and then you can run the script to create a full PDF documentation of your model.
So that PDF documentation does not just have the physical layout of your model. At the bottom of each page is a summary of the calibration and probes parameters on each page, along with, if you put some calibration tuning notes or something in there. So that shows up in the PDF. That's the documentation of your model. We had a question, what are the parameters that are needed to be set for code generation? Actually, nobody ever deals with this. If you generate a model using the MotoHawk project, the settings are all set up for you automatically. And if you drag in a MotoHawk target definition block, those are set up also, the Simulink coder parameters. You can look at them under the under simulation code generation options, but nobody ever really has to deal with these. It's handled automatically for you. And then there's a question, how do we generate AutoDoc? I would refer you to the documentation that comes with the product, but it's either a script or a GUI that it depends on which version you get, that allows you to generate that PDF, by pointing it at your model. Question about, are there any good references on working with non-volatile memory on the wiki? I don't believe that there is an application example that I can think of for that. So we'll have to. That's a good question, and definitely something that people do have questions about. So that's a good one. Joe, can you speak a little bit about if you have multiple top-level rates and you want to have data transferred between those?
Yeah, so that's a good question. Whenever you have, so if I had two different subsystems triggered by the MotoHawk function triggered at two different rates, and I was passing data, you can pass it just through the bus. You put all the data on the bus creator, and then you have a data bus, and you can just pass that. And the one thing to keep in mind, it will, since you are dealing with different rates, typically any data that's moving from one subsystem to another definitely results in RAM automatically there, just because it needs to be remembered moving from one to another. But it will only increase RAM with the variable you actually use, so it's not going to, even though you have a lot of data on that bus, if you only use a couple of variables on the different one model or another, that's where you'll see a RAM increase. You can also use, you could also use data reads and writes to do that as well. Okay.
Okay, a couple last remaining questions. Is there any difference in saving models using the MDL or the SLX? So I think around 2012 timeframe, maybe 2013, MathWorks created a new file format for the models. I think they mentioned some improvements, but from our perspective, and I don't really notice any major advantages or disadvantages. One advantage that that I like with the model files is we put the models into our revision control system, SVN, and when I check in a model or I look at it, check in from somebody else, since I'm kind of familiar with the syntax of the MDL file, or at least if you look at it and you're not, you can kind of tell how much of the model was changed because it's a text format, so it's a text file. I can look at a diff of two models of different revisions and kind of tell, if it was a minor tweak or even where things were changed in the model. Not necessarily able to tell, what blocks were moved around or whatever. I can get a general idea of how much was changed, and that's useful. The SLX format does not really I think you have to buy another tool from the MathWorks to do that, the diffing of the models. Okay, I think that's all the questions that we have right now. Really want to thank you for joining, and appreciate your questions. We had a really good good amount of questions and some interesting topics to discuss. We're doing webinars pretty regularly, so I'd say go to our website, and there's a webinars tab, and you can see what's coming up. And feel free to join for the next one. Thank you.